All right, folks, we're back at the SES Honorary Symposium. We had a little bit of a technical difficulty. Professor Zhang, who was supposed to speak, had some difficulties on our side, and so we're trying to resolve them. So the plan is we move on with the rest of the session, and then we will make time at the end of the session to accommodate her talk. Hopefully, the problems on her hand will be resolved by then. So we just move on with the next speaker, Arif Masud from the University of Illinois at Urbana-Champaign, who is also one of the new 2020 SES fellows. And the title of his talk is Chemomechanical Coupling and Material Evolution in Finitely Deforming Solids Permeated with Reactive Fluids. So, Arif, the floor is yours, and I'm going to get out of your way.
Thank you, Stefano, for the very kind introduction. It's an honor for me to be here today and participate in the Fellow Symposium of SES. And I also want to thank the Society for this award and for its confidence in me. Today, I'm going to talk about chemomechanical coupling and material evolution in finitely deforming solids permeated with reactive fluids. I'd like to acknowledge my graduate student, Masud, who is working with me at the University of Illinois at Urbana-Champaign, and Dr. Rick Hall at AFRL, and Professor Rajagopal at Texas A&M University. Physical problems that involve the transport of chemically reacting fluids through deformable solids. They are present in different fields of engineering and sciences. For example, a typical class of problems is that of additive manufacturing, in which we have engineered material systems that are comprised of fluid and solid constituents, where fluids diffuse through and chemically react with the solid and transform the solid and lead to its material property evolution. These problems also arise in biological systems, for example, in the modeling of tissue or in the modeling of cancer cells. Then we have chemically reacting constituents, where mass exchange takes place between constituents, between the fluid and solid systems, and that gives rise to changes at the smallest level. It leads to microstructural changes. These problems arise in densification of matrix systems, for example, in ceramic matrix composites, where we add small particles, and then through slurry infiltration process, and then through chemical reactions and temperature, we merge them into one solid substance material. We also have thermomechanical coupling processes in material evolution. For example, as shown here, this is the case of battery swelling because of chemical reactions and failure of a smartphone battery. And these processes, thermal, chemical, mechanical coupled processes, where chemical reactions are taking place, they're advancing fronts, oxidations taking place. These are also present in microelectromechanical devices and materials. So the common feature in all of these problems is moving reactive fronts across which the material is changing from one stable state to another stable state, but the mechanical material properties of the constituents can be substantially different across the moving interface. Now, in these problems, because of the moving fronts, because of chemical reactions, because of steep gradients, solving these problems, they pose challenge to numerical methods. And the complexity of the situation increases in terms of if the mass exchange rate is large, if the deformations are large, or the rate of reactions are large. So today I'm going to talk about a variational multi-scale class of methods that can be developed for the problem classes that I mentioned here. And we are going to adopt a mixture theory model to look at this problem. So let's look at a two constituent mixture. One is a solid and the other one is a fluid. And in mixture theory, we assume that the constituents co-occupy the same spatial domain. For example, in this particular case, we represent the density and volume of solid by rho s and Vs, and for fluid, rho f and Vf. So we do not model each of the individual constituents. Rather, we represent these constituents through governing equations, the respective models, the balance laws, and we develop interactive force fields that provide information to one constituent about the existence of the other constituent. So these balance laws are written independently for each constituent of the mixture. And in this framework, we do not model the geometrical microstructure, which can be very expensive from a computational point of view. Rather, we implicitly account for the interaction through the some terms, mathematical terms, which I will explain in here. So this micrograph shows cross-section of fibrous material. We see fibers, and if you look at a portion, take a small portion here, this is different from if had we taken a small portion from. So there is local homogeneity, but globally it is inhomogeneous. And so the mixture theory that I'm going to present is going to accommodate this particular feature. That is going to be pointwise inhomogeneity in the domain will be fully accounted for. So as I mentioned, that we represent each of the constituent by its own balance laws. And in the present model that we are discussing, a fluid infused through a solid, deformable solid. So we have fluid balance of mass equation and fluid balance of linear momentum equation. And likewise, we have solid balance of mass and solid balance of linear momentum. And our objective here is to develop a framework in which the fluid can move relative to the solid. So we do not want to look at it from a constrained mixture point of view. Rather, we want to develop a framework where the constituents can move with respect to each other. In addition, we want the constituents to share mass or exchange mass between the fluid and the solid subdomain. So we introduce this mass reaction term, MF, and likewise in solid. And since it's a system in which the constituents will exchange mass amongst each other, so the mass lost by the fluid is the mass gained by the solid. But this is also going to give rise to some interactive effects at the fluid-solid interfaces in the constituent framework. Likewise, as the fluid flows past the solid objects, let's say fibers, it's going to introduce some drag forces. So we need to bring those effects, the interactive force effects, in the balance of linear momentum equation for the fluid. And it is brought in through interactive force field as shown in here. And according to Newton's third law, then this is equal and opposite to the force field that the solid constituent experiences. And since we are interested in flow of fluid through the solid, so solid is going to provide a domain in which the fluid is going to move. So think of it as a sponge and the fluid is moving through that sponge. If depending on the velocity of the fluid or the rate at which the fluid flows, we can have high advection, local high advection terms. So we have written it in the fluid balance of mass and fluid balance of linear momentum equations have been written in an arbitrary Lagrangian Eulerian framework where the Ale-based material time derivative is shown in here. And that gives rise to these two domains. So Vm is the velocity that is now facilitated by the confining solid domain. In these equations, rho represents the density, alpha will be fluid or solid, as the case would be for the different equations. V is the velocity, T is the Cauchy stress, M is the mass transfer, and I is the interactive force field. So we develop the constitutive equations by first defining the Helmholtz free energy function for the fluid and for the solid. And then following the standard procedures, we get the Cauchy stress tensor for the solid and for the fluid, where the mechanical deformation, the first term here is the mechanical deformation part. The second portion is the solid chemical potential. And likewise, we have the fluid chemical potential and the viscous stress term. In here, the solid has an elastic part and a chemo-mechanical coupling term that arises in here. And that gives rise to gamma is the chemo-mechanical coupling term. It provides the chemical reactions and links it with the mechanical deformation. So with this, we can develop our constitutive model for the fluid and for the solid. And in addition, we get the interactive force field, and the dominant components of the interactive force field that we are going to use in our numerical model here are the mass transfer induced drag force and the viscous drag force because of the relative motion between the fluid and the solid constituents. We can develop the corresponding weak form by first defining the appropriate spaces of functions for the unknown fields, which in the present case is the fluid velocity, fluid density, and the solid displacement field. So we define the appropriate functions. These are typical H1 functions, and we develop the weak form for the fluid mass balance, fluid balance of linear momentum, solid balance of linear momentum, and here are the state vectors. In these equations, if the advection of the fluid, the rate of flow is higher, then fluid mass becomes an advection-dominated problem. If the reaction rate is faster, it becomes a reaction-dominated problem, and that gives rise to internal layers of boundary layers. So both these problems give rise to internal layers, sharp layers, and they pose challenge for the numerical techniques. And today I'm going to talk about how we can develop a numerical method, and the method is variational multiscale method, to address these issues. If you look at the fluid balance of linear momentum equation, it is advection, diffusion, reaction equation. If the diffusion is not dominant or reaction is dominant, it again gives rise to boundary layer effects. If you look at the balance of linear momentum for the solid, it is a diffusion reaction equation because of the zeroth order term, or zeroth order operator on the interactive force field. This interactive force field by itself is a highly nonlinear force field, high nonlinear field because it is a function of the constitutive models. It's also a function of the chemical reactions that are taking place. This is a highly nonlinear term, and if this term becomes dominant, then even the solid balance of linear momentum equation also can give rise to steep gradients. So in order to develop the method that can handle this whole range of problems and can handle the singularities that can appear or the steep gradients that can appear because of advection dominated nature of the problem or the diffusion dominated nature of the problem, we are going to use stabilized finite element method, and I'm going to develop stabilized method based on the variational multiscale ideas. So multiscale framework, the underlying idea of the variational multiscale framework is that we decompose the underlying unknown field into a coarse scale field and a fine scale field. So from a mesh finite element point of view, method point of view, one can think of coarse scales as the scales that can be resolved by a given finite element mesh, and fine scales that are beyond the resolution capacity of the mesh. So what is beyond the resolution capacity of the mesh is the error. Error is also a solution to the problem. So our objective is, can we develop models for fine scales so that we can account for the physics, which is otherwise going to be lost if we are doing calculations on cruder meshes. So can we develop a method that can account for these fine scale effects? And in order to do that, we do a multi-scale decomposition of the problem. This VMS framework leads to a coarse scale subproblem and a fine scale subproblem. And the key idea of the variational multi-scale method is to solve the fine scale problem and extract analytical models for the fine scales. If we cannot find the analytical models, then we can use numerical techniques to find fine scale representation or fine scale estimation and then plug it into the coarse scales. That is the general idea. So non-linear fine scale subproblems help to develop our fine scale models, and I'll show it with the help of an example problem. See, fine scale models are then variationally injected into the coarse scale problem, and that is what we say mathematical multiscaling. We embed the missing effects in terms of fine scale models developed through analytically solving the fine scale variational problems over the sum of element interiors and then injecting the effects into the coarse scale problem. This gives rise to a cost-effective way of solving the problems and accounting for the missing physics. And we do not have to resort to multi-grid techniques, which can be computationally very, very expensive. So this is, in this framework, we can bring in models that represent physics at the finer level. So fine scale also provides us a mechanism as a mathematical zoom to look closely to the material and be able to derive models and bring in constitutive equations, constitutive models that represent the behavior of the material at that level. In order to describe this whole mathematical construct, let's look at this abstract problem. L is the governing equation, U is the unknown field, and F is the source field. In the context of, let's say, elasticity, L is the operators of the elasticity equation acting on the displacement field. We can develop the standard weak form by defining appropriate weighting function integrated over the domain. And this is the weak form, which is the basis of the standard Galerkin method. Now, with a good method and decent mesh, we are able to capture physics, which is resolvable on that mesh. For example, if we want to capture this feature, this this sine function with this oscillations with a decent method, depending on the resolution capacity of the mesh, we will be able to capture the mean solution as shown in here, but fine fluctuations can be lost. Now, if these fine fluctuations that tell us about the microstructure behavior at that element, at that spatial location, if this is important, then the conventional wisdom is to refine the mesh and we will be able to capture the fine features. One can always do that. However, we realized that this can very quickly exhaust the computational platforms that are given to you. So we ask ourselves a question: is it possible that we can develop a numerical method that can capture the coarse scales and account the effects of these fine scales while we are doing calculations on cruder meshes? And that is what I'm going to show here. So we assume a scale decomposition of the unknown field into coarse scales and fine scales. Fine scales are also can be viewed as errors because they are lost on a given discretization. Error is also a solution to the problem. So we can take this additive decomposed form of U and plug it in the weak form. If this is a nonlinear equation, then this scale decomposition should be viewed in the sense of projections. Whether equation is linear or nonlinear, this equation is always linear with respect to the weighting function slot. So we split the weighting function into coarse scale and fine scale parts. And then employing the linearity of the weighting function slot, we can split this equation into a coarse scale problem, which is weighted by coarse scale weighting function, and a fine scale problem, which is weighted by the fine scale weighting function. Think of it that we are solving a nonlinear problem. We go from step n to n plus 1. So we have the solution from step n, and we want to solve the problem at n plus 1. So as we go into the next load level, we have the coarse scale solution from the previous level, and we can figure out how accurately did we calculate our solution at the previous step. So U bar known, we can take it to the right-hand side, and we realize that actually the fine scale problem is in fact driven by the residual of the Euler-Lagrange equations of the coarse scales. So fine scales are proportional to the residual, and if you have a mesh, or if you're solving a phenomena in which your mesh is fine enough to get you all the physics, then fine scales, there are no fine scales, there are no errors because you have solved the problem. So U prime, fine scale, will automatically get wiped out. So it means this approach is variationally consistent. This will satisfy the strong form, the exact solution as well. So we take this fine scale and plug in a coarse scale problem, and we get this modified form, which I've color coded. The terms in the black are the standard Gherkin terms, which were there in the beginning, and the two new terms have appeared, and they have appeared because of the assumption of fine scales. These terms are going to model the effects of fine scales while we are still doing calculations on coarser meshes. And I'll show that when we proceed with this line of thought, it provides us numerical methods that have enhanced stability properties. This idea was first proposed in Hughes' paper in 1995, and then in later works, we extended it to the approach where we can use, we can exploit the fine scale structure of the problem and derive the stabilization parameters, which in fact are embedding the physics into the formulation. And this paper was presented in CMAME in 2008. So let's look at this example problem from the perspective of mass balance equation, which is a diffusion advection reaction equation. This is the advection term, this is the reaction term, and we need to have stabilized methods to account for the steep layers that can arise in either of the cases. We assume an additive decomposition of the mass into coarse and fine scales, and likewise the weighting function associated with it into coarse and fine scales gives rise to a coarse scale problem and a fine scale problem. And objective, as I mentioned, is to solve the fine scale problem and extract an expression for the fine scale density, which can then be substituted into coarse scale, giving rise to a stabilized method for mass balance equation of the fluid. In order to do that, we write the fine scale equation for mass balance in a residual form. R is the residual of the Euler-Lagrange equations for mass balance. And what we say is that we expand these functions, these fine scale fields, in terms of Hubble functions. And fine scale problem, in fact, is more involved, is as hard as the coarse scale problem. So we need to make some modeling assumptions to make it to be able to find the expression for fine scale. So we say that we are going to use bubble functions, and these are functions that become zero on the element boundaries. So what they do is they help us localize the problem to the element interiors, and we can then either use analytical tools or we can use numerical methods to find an expression for the fine scale. So what we do is we substitute this expanded form in the form of bubbles, the density and its weighting function in the coarse scale problem, into this fine scale problem, and solve for the fine scales. And we see that the fine scale, so their model comes out, fine scale is proportional to the residual of the corresponding Euler-Lagrange equation. We substitute this rho tilde into the coarse scale problem, and we get this stabilized form for the mass conservation in fluid. The terms, the top row is the standard Gherkin terms. The second row are the terms that have appeared because of this assumption of fine scales, and it is going to provide us stability. And these ideas were presented in these papers. So we can follow along this line and develop a stabilized formulation for fluid velocity. This is the standard Gherkin term, and the second term here, second row, represents the stabilization terms, where R is the residual of the momentum balance equation for the fluid, which is different from the standard equation, because now we have the interactive force field, and this interactive force field tells the fluid constituent that there is a solid constituent coexisting with it in the domain. Then we have this additional term where the psi parameter, these can be analytically derived, and we have done this derivation. So this is the stabilizing term, and in the process, this stabilization tensor also appears, and this tensor here we can see that interactive force field appears in this expression, and B are the bubbles expression for the fine scale bubbles. So what we see is that the assumption of using fine scale bubbles only resides in the definition of tau. Nevertheless, the explicit expression for this parameter or tensor can be derived, and this embeds the missing physics into the formulation. So we have used a simplified form of tau where we only keep the dominant terms in the denominator of this parameter, and with the reduced term, we get the modified stabilized form for fluid velocity, and we have implemented that in our numerical methods. So first numerical simulation that I'm going to show you is slurry infiltration in ceramic composites. Here there is a ceramic preform, and there is a liquid that brings in silicon dioxide particles. It is normally in the form of water. It deposits under the particles get deposited under gravity. We repeat this cycle a few times, and that helps in reducing the porosity of the material, and eventually the material is heated up to make one continuous material where chemical reactions help increase the density of the material. Here is the process increase in the solid volume as a function of the slurry infiltration cycle. So in each cycle, as the particles come in, fresh slurry material comes in, it's laden with more particles, so there is rapid increase. And then as the particles get dropped, the rate of increase in the volume fraction of the solid decreases. So next, a fresh cycle is repeated. So this process, this model can be used for slurry infiltration. The next numerical simulation is chemomechanical coupling in a mean background temperature that is sufficiently high so that it helps silicon carbide react with oxygen to give rise to silicon dioxide. And so this is the specimen. The material is open to outside oxygen. Oxygen diffuses through the solid. There's a chemical reaction that is taking place. This advancing front moves in, so reacted material and unreacted material. This simulation shows the reaction front that is diffusing from into the unreacted material, and material is transforming rapidly across it. These lines here show the advancing front for different mechanical material properties. Very steep front, but we are able to capture it without any overshoot or without any undershoot. Here are the comparison with the experimental data of oxide thickness as a function of time. So stabilized methods provide us a mechanism to stabilize the moving reaction fronts across which the mechanical properties are varying rapidly, and the geometric deformation is substantially large for this problem. The next numerical problem is a silicon wafer bending problem, typically in electronic structure modeling. It's again, silicon reacts with oxygen. So the top surface is exposed to silicon, it expands. Expansion is about two times the original volume. So substantial change in length in the top. Since the material is contiguous, you can see the advection front moves from unreacted into the unreacted zone. This yellow line moves down. And because of this, there is local bending moment that is produced, giving rise to this large deformation. We have plotted the stresses for this case and done comparison with some published results in the literature for equivalent deformation. The next test case is the bird's beak problem. This is a typical problem in electronic industry for manufacturing transistors. So we have silicon substrate, which is masked by silicon nitride, which is impervious to oxygen. And as oxygen diffuses, material front moves forward and silicon dioxide is produced, which is substantially larger in volume. So we're going to look at this steep front that is moving across the domain. Here are the snapshots of the in the reference configuration of this front, and we see that we can capture it with a very smooth profile. Here are the snapshots of the stress sigma 11 for different points in time along the evolution of the problem. This slide shows the X and Y displacement at these points 1, 2, and 3. For example, here we have snapshot of the vertical displacement at 1. Red are our results and blue are the results in the reference. We get a good correlation. However, the two models, material models, are different, so we see some variation, but overall the response of the two models is fairly consistent. Here is a snapshot at one of the points along the deformation, so frozen in time. So we have von Mises stress distribution. This is the advancing front. This is the temperature change, and we see that temperature is higher in the region where the reaction is taking place. We also see that the residual is also higher in the elements that are being traversed by the advection front. And since I showed you that variational multiscale method, the fine scales are proportional to the residual of the Euler-Lagrange equations. So fine scales are also higher, or these fine scale models are capturing the missing physics in this part of the domain where the residual is higher. And these kinds of problems are typically solved with considerable mesh refinement with mesh moving techniques. And we have shown you a stable response of the advancing front of the material across which the material is changing from silicon to silicon dioxide. And we get a very smooth profile on just very first mesh that we created. We are now extending it to thermomechanical problems for which we need to write the Helmholtz free energy function as a function of temperature field. This gives rise to constitutive equations where the Cauchy stress for the solid and the fluid is also temperature dependent. In addition, the mass conversion rates are also temperature dependent. So we need to solve for an energy equation. We need to add this energy equation to balance loss for the fluid and for the solid. And this gives rise to significant coupling effects. And I will show you the results that will account for chemomechanical coupling, which means extent of reaction-induced deformations, mechanical deformations. Thermomechanical coupling means temperature-induced deformations of thermal expansions and contractions. And thermochemical coupling, which means temperature-induced because of the reaction rates. Reactions can be exothermic or endothermic, and that can locally change temperature across the moving front. So here is one problem where we have an unoriented material at time t0. Oxygen is provided at the right end. It infuses. Material is completely transformed. Reaction is taking place here, but it has not oxygen has not reached the other end, so it is untransformed material. Here, the entire material has gone transformed from unoriented to oriented material, or untransformed to transformed material, and now thermal relaxation has taken place, and so thermal shrinkage. We can show this thing: initial state, mid-reaction state, depleted state, and steady state in the as a function here. So this blue line shows time t0, unoriented material, unreacted material. At a later state, which is the initial or mid-reaction state, where there is more reaction taking place here, we see higher stress in that region and low stress in the region where reaction is not initiated yet. Entire domain has transformed, so there are stresses built inside the material, which eventually, these are thermal stresses, because thermal phenomena has not got enough time to get dissipated, and eventually it gets dissipated and we get the steady state. We can also look at this phenomena from the point of view of fluid concentration. On the right end, fluid has fully permeated, but it has not yet reached this end. So the fluid concentration is 0 there. Likewise, temperature is higher where the action is taking place and lower on the other sides. And this parameter here is the reaction state variable. When it is 0, it means this material is completely depleted at this particular point, and 1 means that reaction has not reached the left end yet. This is another test case where we are looking at mechanical material properties that actually give rise to a steeper front under thermal oxidation. These are different states, and we have plotted oxidation thickness as a function of time. Solid line is our numerical results and comparison with some published results in the literature. Also, we have looked at oxidation growth rate as a function of thickness, and again, we get good correlation with published data in the literature. So as my concluding remarks, I would say, I've presented a mixture theory model for coupled thermomechanical response of material. And mixture theory model behaves as a reduced order model because we are not individually modeling each of the constituent, which in this discussion was fluid and solid. Rather, we are bringing the effects of their interaction through interactive force fields. Each of the constituent is modeled with its own governing equations or its balance laws. The model also accommodates pointwise inhomogeneity in the material, while it accounts for the inter-constituent interaction via interactive force field, which appear because of the local force balance in the evolution of the material. As the material is being formed, mass is being changed between the constituents. That gives rise to mass exchange-based interactive effects between the constituents. If the fluid constituent flows relative to the solid, then there is viscous drag coefficient that gets induced on the solid and vice versa on the fluid. I've also presented you a stabilized method for solving these class of problems where different constituents are evolving with their own balance laws, and there are reaction fronts, could be advection dominated, could be reaction dominated. And I developed the stabilized method based on variational multiscale idea, and variational multiscale idea from the perspective of the SES society, where we are looking at the modeling of the material. Variational multiscale is not just as a method for stabilizing the numerical techniques, it is also a method to build in fine scale physics, which is otherwise lost when we do computations on cruder meshes. We are invariably forced to use meshes which are cruder because the phenomena could be fine grained, and so invariably for the physics, any given discretization, because the reaction fronts move as a function of time, and depending on the rate of reaction and intensity of reaction, we can produce very thin layers. So invariably, for all practical purposes, we always are working with meshes which may not be fine enough for the physics that we want to capture. And so variational multiscale method provides us a mechanism or an avenue to build missing physics. So in summary, mixture theory model serves as a physics-based reduced order model that without accounting for or modeling for each of the constituent, we are still able to account for the mass exchange, the drag forces, the reaction rates, the advection of reaction front, and local microstructural changes. And stabilized methods provide an avenue to get computationally economic solutions for these complex problems. And with that, I thank you all.
Well, thank you, Arif, for a nice presentation. And also congratulations again for your SES fellow status.
Thanks.
So let's see if there are any questions. Let me refresh the page to see in the live feed questions. Yes, we have Hamed Aftabaradaran, if I pronounce it correctly, says, do you think the model would be applicable to lithium-ion batteries?
Yes, very good question. That was one of the viewpoints that we had. So in lithium-ion batteries, you will have to model the convection of ions. And so you can add an advection equation to model that. And that advection equation will have the advection type terms that I talked about. So you will be better. You can definitely model with it. So lithium-ion batteries will give rise to swelling. So the kind of problems that I was showing to you, you can absolutely do that. And the advection term or equation that you will add for the concentration. So if you will have as many advection equations as you have species in the system. So the system can become very intense very, very quickly. And you will need stabilization techniques, and the ideas that I presented, you can definitely apply it there to model this framework, these kinds of problems.
Okay, let's see if there's any other ones. Okay, I don't see one right now, so maybe I can just ask one follow-up. So at some point, if I understand correctly, in your conclusions, you were talking about the fact that you can capture relatively fine physics with relatively coarse mesh, right?
Yes.
What is the limit of that statement? So what is the kind of situations where this capability would break down?
Okay, I'll give you an example. One can look at the microstructures. Let's say, think of it, let's say in fluid mechanics, and think of turbulence. So you, given a mesh will have a certain modeling capacity. Beyond that, you have rotating motion, and your mesh is not able to capture it, so we can develop a model for that. But that model will also have a limit, because there is a still smaller vortex and a still smaller vortex and yet a smaller vortex. So yes, there will be a certain limit to which, for a given mesh, yes, you will be able to go beyond the resolution capacity of the competing methods. But the fine scale model will have its capacity to be able to bring all those fine scales that you completely missed in the coarse scale physics. So yes, you will need to take a look at it from the point of view of engineering accuracy, and you can determine based on that. So idea is, don't start with the finest mesh to begin with. Start with a crude mesh and see if you are getting the accuracy. Compare your results with the experimental data. And if you're getting the accuracy, that is a good point to stop. You can always refine the mesh and you'll get better. When you refine the mesh, what you are doing is you are making life easy for your fine scale model, because your fine scale physics is now part of the coarse scale physics.
Thank you.
Somewhere in between.
Thank you. I don't see any other questions, so I guess we can stop here. So Arif, thank you again for your presentation.
Thank you, Stefano, and I thank the society once again. Thanks.
And we wait for the next speaker to come from the backstage.
Thanks.